Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're tackling a problem on thermodynamics. This is an advanced problem in the pure substance section. And here we have a situation in which we have water, and we're given all properties from the first state, and then a handful of property of the second state, and we need to define the second state to be able to calculate the difference as per usual. Now, this requires you to understand very well how pure substances work. So if you are not comfortable with this yet, just jump into the previous videos in which we tackle these problems, the simpler ones, so that you can understand how these things work. So the problem statement reads, a piston cylinder device initially contains 50 liters of liquid water at 40 degrees Celsius and 200 kilopascals. Heat is transferred to the water at a constant pressure until the entire liquid is vaporized. A. What is the mass of the water? B. Find the final temperature. And C. Determine the total enthalpy change. And last, D. Show the process on a TV diagram with respect to saturation lines. So let's firstly draw what we have here. We have a piston cylinder device. So let's just draw a simple box with a little piston here. Okay. And then inside this guy we have water. So we're dealing with water. So you already separate the water tables that you know we're going to need them. If you need the water tables, I've left links for you here on the description of this video. And then we're going to add heat to the system, and we're going to have something similar. But because this is a piston cylinder device, this means that this part of the device can move, and therefore we expect it to rise, right? Because we're giving energy to this piston cylinder device. So we're giving heat from state 1 to state 2. That's what's happening. Now, on this first state, we know we have 50 liters, that's the volume. We know we have 40 degrees Celsius, that's the temperature, and we know we have 200 kilopascals, that's the pressure. On the second one here, what do we know? Well, we know that this was a constant pressure process, so therefore this has also to be at 200 kilopascals. And we know that this was done until the entire liquid was vaporized. So what does that mean? It means that if you remember the TV diagram, let's just do it one quickly here. T for temperature, V for specific volume, and we have it down there. This is a constant pressure line. We are right there, right? So right at that point, put in red, right? So we're right there. Why? Because that's the point in which the entire liquid is vaporized. That's exactly the definition of that point, right? It's a point in which we are at a saturated vapor state. So we have saturated vapor state. Any additional energy I give will make this go into a superheated state. Any energy I remove will incur in droplets of liquid forming, right? So that tells us that we are in a saturated vapor state. Okay, and those are the two pieces of information that I have for state 2. Okay, so we need to explore this state a bit more before we can completely get its properties. So we can start with part A, which says what's the mass of water, and that's relatively simple because on this state, let me go ahead and copy this whole thing here. On this first state, we have everything we can possibly need, right? So let me put it over here. If we're trying to find the mass, remember that the specific volume is simply the volume divided by the mass. So therefore, if I want the mass, what I can do is I can take my volume and divide by my specific volume, and I'm going to have the mass. The volume I already have, that's the 50 liters there. We had it from the start, all good. And then the specific volume I can grab because I have the state completely defined. I have the temperature and the pressure. So what I'm going to do is I'm going to jump into my water property tables. Okay, I'm looking at the saturated water. I don't know yet whether state 1 is superheated, compressed, or saturated. I'm about to find out. Okay, so I'm going to look in the 40 Celsius row. Here it is. And I'm going to know the following. Okay, at 40 Celsius, my saturated pressure is 7.1 kilopascals. I'm at 200. So that means I have a compressed fluid, right? So I'm remembering again this drawing here in the zone. I'm in this region here. I have a compressed fluid. Another way to do this, let's do the same thing, but now instead of looking at the temperature table, let's look at the pressure table, okay? Exactly the same analysis. Here I am, pressure table. Now I'm going to look for 200, which is our pressure. 200, here it is. This is the row we're looking for. And I can verify that the saturated temperature is 120 degrees Celsius, and I have 40. So the other name for a compressed fluid is a subcooled fluid, right? So it's a fluid that is at a temperature lower than that of the saturated temperature. So we know, you don't have to do both tables. I'm just showing you that there are two ways to do this, but we're 100% sure that we have a compressed fluid. Okay, so let's write that down for our own sake. So state 1 is a compressed fluid, or you can also, or a subcooled fluid, same thing. Okay, you're going to see different books call it different things, subcooled or a compressed fluid. Okay, so what does that mean? Well, that means that if we want to grab properties for this fluid, I need to first identify whether my pressure is big or not. What is big? Well, rule of thumb is the following. If my pressure is smaller than 5 megapascals, okay, then I can use the saturated liquid properties. Or in other words, I can approximate, I can approximate to the saturated liquid properties. Okay, so what does that mean? In our case, we have 200 kilopascals. Okay, so we have 200 kilopascals. That is smaller than 5 megapascals, right? Absolutely smaller. And therefore, it's all good. We're going to grab all properties from the saturated liquid. Okay, so what do I mean? Let's do that in practice to see what I mean. If I go here to, and I'm always going to use the temperature table to avoid, because I can minimize the error, okay? So whenever I'm approximating to saturated liquid, I'm aiming for the temperature table. I'm going to go ahead and I'm going to say that this row that I highlighted, this yellow row here, contains the information for my state 1. All the ones that are talking about saturated liquid. So this guy here is approximately my specific volume. This guy here is approximately my internal energy. This guy here is approximately my enthalpy. And this guy here is approximately my entropy. Okay? We're doing that because our pressure is not that great. And I'll show you that. I'll show you that in practice. Okay? So that means that my specific volume is, according to my approximation, 0.001008 meters cubed per kilogram. Okay? Just for the sake of showing you how close that is or not to our approximation, I'm going to go down all the way to the compressed fluid tables. Okay, so bear with me. I need to jump through all the saturated tables, the superheated tables, and eventually we're going to reach the compressed fluid tables. Okay, so compressed liquid for water. First, note that it starts at 5 megapascals, precisely because of what I just said. Okay, if it's smaller than 5 megapascals, you don't really need these tables. That's why you don't have any information here for 200 kilopascals, 300, and whatnot. Okay, and then if we were at a pressure of 5 megapascals and we look at the 40, which is what we're doing here, this is the temperature we are at, you'll see that the specific volume is 0.001005. 7. Remember the hours that we just got approximated was 0.001008. Okay, so the difference is only in this last digit here. Okay, and it's not that big, by the way. So bottom line is, your rule of thumb, if the pressure is smaller than 5 megapascals, don't bother with this table here. You don't need a compressed liquid table. You can approximate your properties to those of the saturated liquid. Okay, so all of that to be able to go back to our equation. Where is our equation? Here. All this to be able to go back here and say, okay, so that means that my specific volume for state 1 is 0.001008. Okay, and that is in meters cubed per kilogram. And what I'm missing here is the volume, and my volume is 50 liters. And obviously there's a problem here because we cannot cancel out our liters with our meters cubed, so we need to convert that. Well, if you know how to do that, that's simple. You can go straight ahead and do it off the bat. That's just going to be 10 to the minus 3 meters cubed. But if you don't, let's walk through a quick way to do that every single time so you never miss it. Okay, so let me just finish off this math. So we get rid of this, and then we're going to be left with the kilograms, which is unit for mass, which is great because we're after a mass for part A. And that gives us about 49.6, so 49.6 kilograms is the answer for this part here. Beautiful. Okay, now what if you are not comfortable converting? Well, let's do it this way. The way that I always think about it, right, for liters, right, I always know that, well, it's easy for me to convert from liters to millimeters, okay, as I know it's just going to be times 10 to the third milliliters. And the other thing that I know, and this I just remember, I guess it's good to remember, is that a milliliter is the same thing as a centimeter cubed. And from this point, what I do is, oh, that's simple for me to convert because I know that for every 1 meter, that's exactly the same thing as 100 centimeters. So as long as I'm multiplying anything by this, I'm multiplying by 1 because these guys are the same thing. So this is the same thing as 1, right? So therefore, no, we're not changing anything. And I can just do that 3 times. And once again. Okay, so what ends up happening is that you get 10 to the 6 here. You have 6 zeros there. So therefore, this is the same thing as 50 times 10 to the third divided by 10 to the 6th. And we're doing, don't forget, we're doing centimeters cubed. And then we have 1 centimeter cubed here and then centimeters cubed here. So these guys go away. We're left with meters cubed. And this is 50 times 10 to the minus 3 meters cubed. Okay, that's how I do it. Especially if I'm doing a test or something like that, I ensure that I do all these steps so that I don't get the unit conversion wrong. Cool, so that's the first part, part A. Now, part B asks us, what is the final temperature? Okay, what is the final temperature? And what I'm going to do is I'm going to skip B and C. I'm going to go straight into D because D can actually help me understand the problem and solve B and C, okay? So let's go ahead and draw the TV diagram with respect to saturation lines because we can do that already with the information we know with this information here. Go ahead and copy this. Let's go down here so we have some space. All right, so TV diagram. We have temperature on the y-axis. We have specific volume on the x-axis. And we have our saturation lines. So like this, okay? And we are always on top of a constant pressure line because we're always at 200 kilopascals, okay? So I'm going to go ahead and draw my constant pressure line. I'm going to choose any line here, okay? And I know I'll go like this, and then go like this, and then when it hits that, it's going to go straight, and then when it hits here again, it's going to go up again, okay? So this is my 200 kilopascal line, 200 kilopascal line. And I could draw other ones, you know, can draw different pressures. This would be another pressure, this would be another pressure, and so on and so forth. But I'm just interested in the 200. Oops. I'm just interested in the 200 kilopascals because I know the process occurs at 200 kilopascals. Now, what do I know? I know that we're starting here at some point, okay? I know we're starting, I'm going to call it here. It doesn't have to be there. I'm just drawing it for the first time so I can actually decide. As long as my state 1 is here in this region, that will be correct. And I know that my endpoint is here from what we talked about before. Okay, so what's happening there is I'm going from state 1 all the way to state 2 like so. What is happening? I have a subcooled fluid in the beginning, and I'm giving heat to this fluid, and as I'm giving heat, its temperature is increasing, as is its volume. Okay, once we reach this point here, we have the saturated liquid. And from this point on, we are saturated mixture. We're increasing the amount of vapor, decreasing the amount of liquid, increasing the amount of vapor, decreasing the amount of liquid, until we reach the point in which we don't have any drop of liquid left. Okay, so what does that tell us about the temperature? Well, it tells us that if we are going to stay in this 200 kilopascal line, first, our initial temperature here we know is 40, right? 40 Celsius, because state 1 is 40. Here it is. Okay, and I know that my temperature is going to be increasing as I'm giving heat to the system, right? It's going to be increasing. My piston is going to be going upwards. That's why I drew the piston here higher than the other one, because it's a piston cylinder system. So as I'm giving heat, the pressure is not increasing because this guy can move freely, but my temperature will increase. and it will increase all the way until it reaches the saturated temperature, right? The temperature at which there is the saturated mixture for both the saturated liquid and saturated vapor, which has to be the same temperature. Note that once we go inside the dome, the temperature is not changing anymore. So what does that mean? Well, it means that this final temperature here, let's go ahead and call this T2. So T2 has to be the saturated temperature at 200 kilopascals, because we never left that line. So what I'm going to do to find out part B, okay, so this is the answer for part D, right? This is the drawing in respect to saturation lines. And what I'm going to do now is I'm going to go into the table. I'm going to go to the pressure table to solve for B and to find out what is T2. What I'm going to do is I'm going to go to the pressure table at 200 kilopascals, and I'm going to read off the table what is the saturated temperature. So let's go ahead and do that. So this is the temperature table. This is also temperature table. And here you go, pressure table. I'm going to look for 200 kilopascals and just read off what is the, oh, we had done already, right? When we were doing our exercise. So there you go. At 200 kilopascals, my saturated temperature, Tsat, is 120.21 degrees Celsius. So I can be sure that my state 2 is at that temperature, because the temperature will increase all the way until it reaches that point, and from that point onwards, it's not going to change until this becomes a superheated fluid, right? And we know that's not the case because we reached the point at which the whole thing has been vaporized. So in other words, part B, and I lost my, there you go, part B, T2 is Tsat at 200 kilopascals. So therefore my T2 equals 120.21 degrees Celsius. And that is my answer for part B. Now, what I can do here, since I know more information now, is I can actually make my diagram a bit better, because I can also place here the 120.21. And that will be right there. What else do I know? I know that this point here, the specific volume here, that is the 0.00108. And this guy here, I can read off the pressure table if I wanted to now. Okay, cool. So we've done A, B, D. We're missing C. And C is asking us for determine the total enthalpy change. All right, cool. So enthalpy is energy. So this is going to be in either joules, kilojoules, megajoules, something like that. We know we have state 1 and state 2 completely defined, so that's not going to be a problem for us. We're going to first grab the enthalpy of state 1, and as I made reference to before, I'm looking for enthalpy. In state 1, I'm approximating to the saturated liquid, so this is going to be my value here, 167.53. That is how much energy I have in the enthalpy for state 1, 167.53. 157.53, 67.53, and that is in kilojoules per kilograms. And for state 2, I need to go to the same place where I grabbed this, and I'm going to grab H2. That's going to be the saturated vapor enthalpy. Where's my pressure table? The 200 is there. Let me continue this line here rightwards, and I'm looking for the enthalpy for the vapor, saturated vapor. Okay, so I'm looking for this guy here, 2706.3. 2706.3 kilojoules per kilogram. Now, note that they ask for the total change in enthalpy. So that indicates they don't want it in specific form, so they don't want it per kilogram. They actually want the value of energy in joules. And we happen to have the mass that was part A of the problem, so we have everything we need, right? So, if I wanted to do, okay, what's the change in enthalpy? What's the change in enthalpy? That's just going to be H2 minus H1, right? So lowercase H2 minus H1, and that's perfectly fine. We just do the difference between these two guys here. If I want uppercase enthalpy, all I'm going to do is I'm multiplying the mass by H2 minus H1 so that I get rid of the mass component on both specific enthalpies. In this case here, this is going to be the 20. So we have the mass as 40. What did we find? 40 something? 49.6. So that's going to be 49.6. That multiplies 2706.3 minus 167.53. Unit-wise, what we have here is kilograms. That multiplies kilojoules divided by kilograms. So our answer is going to be in kilojoules. And then number-wise, what I got here is 1.259 times 10 to the 5th in kilojoules. That's very big numbers for us to have in kilojoules, so we can go ahead and transform that into megajoules. Get rid of the 3 here, and that's just going to be approximately, just do approximately 126 megajoules. And that's going to be our answer for part C. Okay, so we done 1, A, B, C, and D. This is a bit harder because you need to understand how this works. You need to have a clear idea of how this works so that you can solve for part B and C. You need to be comfortable with identifying the states. You need to be comfortable with this idea here of approximating properties to the saturation liquid, as long as you have a subcooled fluid or a compressed fluid. And the pressure is not that great, smaller than 5 megapascals. So, there's a lot of things that you need to understand and be comfortable with to be able to solve this problem here. If you have any questions, as per usual, just leave them down below and I'll be happy to address them. If not, we'll talk soon. And if this helps you out, consider liking the video, and we'll talk soon. Bye-bye.